All right, so I printed out a copy of the of that document that I asked you. Did I ask you to bring that or no? No? Never mind. It's there anyway. Who cares? Okay, so I'm going to pass out pretty much all the work that I have for you all. The grades on Canvas should be updated. It should reflect everything that I have for you, including if you came and met with me. I changed your first grade to 100. The only thing I haven't done is added the 5-point bonus to the final because we haven't taken one. Yes?
So this is on Canvas too.
That's on Canvas.
So we can use
you can use that, yes. There we go. Thank you. All right, so the document that I'm giving you right now can be used on exams, but you're not going to actually need this document for the test on Wednesday. All right, so you don't need it, but I wanted to use it today while we're going over things. We are going to talk about the next section, 8.2, today, and then the test will only cover up through 8.1. So the application one, that's the one where I showed you like the center of mass thing real quick. That won't be on the test. That was more just to show you like at least one thing you could do. So the test will only cover through 8.1. That doesn't mean don't do your homework, and that doesn't mean don't pay attention, all right? We'll talk more about the test at the end, yes?
Just up to including 8.1?
Including 8.1, yep. So I will show you at the end of class what to expect for the exam, all right? All right, so we are going to start 8.2 today, which is titled Series. All right, so to motivate this idea, I want to start out with an example. And let's take, let's do that right there. So that is called a what? That is a sequence, right? That is a sequence. And obviously that is not a series, so we need to figure out what the difference between a sequence and a series is. If I were to actually start to write out this sequence, I'd start out by plugging in n is 1, right? I would get 1 over 1 squared is 1, and then 1 over 2 squared is 1/4, and then 1/9, right? 1/16, and so on and so forth. And this is an infinite series, right? What we're interested in is not talking about whether or not this converges or not. So in your homework for 8.1, the question would have been, does this sequence converge, right? So does this one converge? If we take the limit as n goes to infinity of the sequence 1 over n squared, does that converge or not? No? Where does that go to? This goes to 0, right? So it converges, right? It converges. So this right here is a convergent sequence. Okay, so everything I've put up here is what we've done, right? So now what I'm going to do is I'm going to define a new sequence, all right? A new sequence. Here's a new sequence. So a new sequence here. And here's what it's going to be. Well, you know how with this sequence here, this one would be, oh man, this one right here would be a sub 1, this one would be a sub 2, this one's a sub 3, right, and so on and so forth. My new sequence that I'm about to define, I'm going to define it as follows. I can't call it A because I'm already using A, so I'm going to call it S. S1, okay? Let me tell you what the first number in this sequence is. The first number is just a sub 1, all right? Which would be what? 1, okay. Then I'm going to define S sub 2 to be a sub 1 plus a sub 2, which would mean I'm going to be taking a sub 1, right, which is 1, and adding to it a sub 2, which was 1/4. And if I add those together, I get 5/4, right? Okay. And then what do you think S sub 3 is going to be? A sub 1 plus a sub 2 plus a sub 3, which would be 1 plus a 4th plus a 16th, right? 1 plus a 4th plus a 16th? Let me see here. I think I have this. Ah, man. Yeah. Pardon? I don't. Yeah, it's something like that. I'm not. I kept it as a fraction. Okay, so I'm having my computer do this for me real quick, and I'm going to do it as a decimal. This would be 1.362. This one was 1.25. And then S sub 4, 1 plus 2, a sub 2 plus a sub 3 plus a sub 4. Y'all with me? Okay, and I'll have my computer do this for me also, and I'll get it as a decimal. So if I go out, 1.424. There might be some rounding here. This is 1.424. Okay, so do you see why I'm using the letter S? What do you think the letter S stands for here? What am I doing? Sums, right? I'm doing sums. So I'm using S to represent the fact that I'm doing a sum, right? Okay, so using this pattern, if I said what's S sub k, then that would be a sub 1 plus a sub 2 plus a sub 3, and where would I stop? A sub k, right? And that would be some number, right? What's wrong? Pardon? Why isn't it what?
3, why isn't it 1 plus 1/4 plus 1/9?
Oh, did I put 1/16? I'm sorry. Thank you. That's because it's Monday. Thank you. Yes, that's 1/9. I apologize. Thank you for catching that. But this should be right because I had the computer do that. Okay? So this would be the sum, right? S sub k would be the sum of the first k numbers of this sequence A sub n, right? This right here is called the kth partial sum. All right? And don't forget that that's going to be very important later, the kth partial sum. All right? So if I said, what's S sub n? You would do a sub 1, a sub 2, a sub 3, all the way out to where? A sub n, right? And we would call this the what? The nth partial sum. So this one would be called the nth partial sum. Kth partial sum, nth partial sum. If I went S sub j, it would be the jth partial sum, right? It's just, this is just a new naming, a new kind of language that we're going to be using, all right? Y'all with me? the important thing to note right now is that when we start with a sequence, right, we can list out the numbers and we can talk about whether or not that sequence converges, right? And in this one, it did. But now what I've done is I've created a brand new sequence. So can't we ask the same question? Does this converge, right? Does this converge to something? What we're doing is we're adding up, we're starting to add these up, and the question on whether or not this converges is asking, if you add these together forever, does that actually go towards a number, or does it get really big and start overflowing? Does that kind of make sense? So how are we going to determine whether or not this converges or not? That's where we're headed, all right? So with that, let me continue this. I would like to continue it below, but I'll have to go up here. Here's another way we could write S sub n. We could use it, a more condensed notation for this. We could say something like, this is equal to the sum, right? That's our sigma notation that we used before. And then we could say, I don't know, we can use anything down here. Let's say k equals 1, a sub k, and then where am I stopping? At n, right? So do you remember with Riemann sums, this notation? They said we're going to add a bunch of things up, right? We're going to start with k being 1. Now what are we actually adding up? This. So we'd start with k being 1, this would be a sub 1. So we'd write a sub 1. And then we say plus, and then we change that to 2, right? We go a sub 2, and we keep doing this until we get to the last one, we stop at n, a sub n. So do you see that this notation right here is a very condensed way of writing the nth partial sum? Yeah? Why do y'all look so confused? Are y'all all right? Or is it just Monday? It's just Monday? Okay. Any questions on that notation? Because I want to start adding these things up, and I want to start with the first one, right? Yeah. So I'm just going to use k equals 1 as my starting point.
Is the number it starts at?
Uh-huh.
Okay.
Yep. Now, keep in mind that when you do this notation with this sigma, this right here is what we call a dummy variable, meaning you can use pretty much anything you want there. So like, that's the same as if I wrote sum, if I just decide to say j equals 1 to n of a sub j. That would be the same thing. Okay, so I'm going to say j starting at 1, then I'm going to replace that with 1, then add 2, 3, 4, and stop at n. So this is called our index, our starting index. This is our stopping index, and that index can be any letter you want. We usually use I, j, k. That's what we usually use. Sometimes we use, well, we also use n, sorry. Okay. All right, so let's get some things, some definitions up here, and then we'll proceed with this example. So given a sequence a sub n, the infinite series, or we might just call it series from now on. We will probably leave out the infinite. The series for that sequence is how should we write this? The sum, I'm going to use n this time, n equals 1 to infinity of a sub n. So notice that I'm for this series, I want to add these up forever, right? That's what, yes?
Why did you use parentheses around series?
Oh, what I'm saying is, this is a definition. This is the definition of an infinite series. Now, if instead of saying infinite series, if you just say series, then it's the same thing. It's implied that it's infinite. Okay? All right. So there's a difference between this and that, isn't there? This is a partial sum. Do you see why they call it a partial sum now? Because you're stopping somewhere, aren't you? But with the series, an infinite series, you're actually adding these up forever. And our question is whether or not that actually goes to something, right? Does it go to something? Yes.
Would the example that we did on the right side, would it technically be a finite series if it stops somewhere?
This would be a finite series, yes, which is why we call it a partial sum, because it adds it up partly. It's not the whole thing. It's like if this goes forever, we stop somewhere. That's part of it, right? Okay, so that's the definition of a series. Now we need to discuss what it would mean for a series to converge. So like, how do we determine whether or not it converges? Do we know, how do we test to see if a sequence converges? Take the limit, let n go to infinity, right? So we want to do something like that for this also, all right? So how do we determine convergence of a series? A series is said to converge or be convergent if the limit as n goes to infinity of the sum k equals 1 to n of a sub n converges. Or I'll just say exists. All right, so what the heck just happened there? What is this? Well, this is the partial sum, right? This is the partial sum. If we take the limit as n goes to infinity, so as that upper index there, if we let that go to infinity, it starts to add these up forever, doesn't it? If that limit exists, then we say that the series is convergent. Okay? Now, how we do that's going to be difficult, but this is what we would need to do, all right? If it does, if the limit exists, then we will say the series converges to capital S, all right? Now, I'm going to write that in more mathematical notation. The limit as n goes to infinity of the sum k equals 1 to n of a sub n equals S.
Isn't capital S notation for arc length?
It is, yes, capital S is used with arc length also, so it can be a little confusing, but you know, that's integrals and continuous nice functions. Now we're talking about sequences in series, so it's kind of a different idea, so we use the same letter. Is this okay? Is all right? This is basically me just saying, hey, if that limit exists, then that means it goes to a number, right? Let's just call that number S. And so we have this, wouldn't we? So our goal, okay, our goal is to try and find S. If I give us a sequence, right? And I say, does the series of this sequence converge? Then we will have to take a look at this limit and see whether or not it goes to a capital S or not. Does that make sense? Okay. Now, just as an alternative notation to this, we could also write this. If we didn't want to write this, we could write this. Limit n goes to infinity of S sub n equals S. Right? Because isn't this the nth partial sum? Isn't that the nth partial sum? And didn't we say S sub n was the partial sum? You can look back in your notes. So this is the same as that, right? And another way we can write it is this. Do you remember what that arrow meant? The arrow meant that it converged, right? Back with sequences, when we said a sequence converged, we'd write a little arrow pointing to the number. Same thing. So this means this means this. All these are the same notations. Clear? All right, so now let's take a look at, I'm going to use the computer to try and see if we can't investigate two particular sequences and see what their series do. All right, so I'm going to erase all this so we can clear the board. So let's go back to that problem that was n squared, 1 over n squared. And I'll write that down over here so you remember what we're looking at here. We are looking at the sequence a sub n equals 1 over, 1 over n squared, right? And we listed out the different pieces of this one already. We already know that that sequence goes to 0 because you just take the limit of that and it goes to 0. Great, fine. But the question is, does it converge? Does the series converge, right? Does this go to some capital S? So on the computer here, what you'll see is on the left side is just the sequence, right? And we said the sequence was 1, 1/4, 1/9, 1/16. So if we plug in 1, we get 1. If we plug in 2, we get 1/4, right? Yes? Yes. Okay, so that's 0.25. And then if you plug in 3, you get 1/9 and 4. And so we know that the sequence is converging to 0. But what is the sum doing? So when we plugged in 1, we got 1, right? When we plugged in 2, we got 5/4. When we plugged in 3, we got another number, right? So look at this sequence. Does that look like it's converging? Well, we'd probably need to go a little further out, right? So let's go out, I don't know, we're 4, here's 5. And the computer is keeping track of the sum for me, all right? So is that converging? So we're out at the 10th one. So I'm having the computers now added up the first 20. It's added up the first 20. We're at 1.596. So is this growing, or is this growing without bound, becoming infinite, or is it converging to something? What is your instinct telling you from the first 20 terms? It looks pretty convergent, doesn't it? So let me keep going. We're at 1.6. It's growing though, isn't it? 1.628. We're almost out to the hundredth number here. 1.634. Doesn't seem to be growing much, does it? So would you agree if it's changing, it's further out here in the decimals? And let me see, I'm out to the 124th one. Let me actually go out. Oh, I'm going to go out. I'm out to the 400th one. And look, I mean, not much of a change, right? I'm at the 400th number. Let me go out 800. I might kind of bring my computer down to its knees here. Let me see. Look, I mean, it still has changed a little bit, hasn't it? But it's taken a long time for it to happen. So visually, it looks convergent, right? This looks convergent, but we have to have a definitive way of proving it. Because, I mean, is 800 a big number? Relative to what, right? I mean, 800 is nothing compared to 8 million. So if I went out 8 million, would this jump up to 1.7? Maybe. So what I'm trying to get at is the visual evidence is not enough. We need a way of doing it, right? Okay, so now let me back this up so it doesn't freak out when I switch this to 400. Let me go out to 100. Okay, so that's that sequence. So what we have here, if we were trying to summarize, we have a sequence, right? It converges to 0. In the series, we think converges, right? We think that this converges. Right? And it's still an open question, right? Let's look at a different sequence, all right? So I want to change our sequence to something else. Instead of 1 over n squared, I want us to just do 1 over n. So that sequence is different, isn't it? So if I were to list out that sequence, it would be 1, 1/2, 1/3, 1/4, 1/5, 1/6, right? And if we start adding them up, we get something. Now, does the sequence converge to 0? Does the sequence converge to 0? Yes, so this is still true, right? This we don't know. So let's take a look at it on the computer and see what happens. Back this up. We'll go out the first 8. Let me change this to 1 over n. There we go. Okay, so we plug in 1, we get 1. Plug in 2, we get 1/2, 1/3, 1/4, 1/5. So the sequence is converging to 0. Let's look at the sum now. So the sum, we're out the first 8 terms right now, or 8 numbers. Let's just keep an eye on that 2.9, 3.1, 3.2, 3.5, 6, 7, 8. Look at the shape of that thing. It does kind of look like the other one, but it doesn't seem to be as dramatic as far as like flattening out. If you were to talk like in terms of like tangents, it almost looks like the slope of this tangent's like pretty positive, right? All right, let's go crazy here. Let's go out to 100. Let's see what happens. Just keep an eye on that number, 4.8, 5.1. Okay, let me go out 400 terms. 5, 6, we're busting through 6 now, right? 6.5, we go out 800. Can we bust out 7 there? Yep. So look at this thing. This seems to be growing differently, doesn't it? And so in terms of convergence, we still don't know, but what do you think? Do you think it converges? Divergent? We think maybe diverges? Question. I mean, we don't know. We don't know. But it looks like it, right? Looks like it diverges. So both of our sequences converge to 0, right? Both the examples I've given you, both sequences converge to 0. But their series appear to be doing 2 different things. Agree? So just because a sequence goes to 0, that is not enough information to tell you whether or not the series goes to 0, or converges, sorry. All right? So just because this goes to 0 doesn't mean anything in terms of this. Now, what if your series, or sequence, what if your sequence up here goes to something other than 0? So let me give you an example. Let's do one more example. Let's take a sequence like this one. N over 2n plus 1. Okay, what does that converge to? 1/2. Now how are you getting that? You would do L'Hopital. So from last class we learned, you get infinity over infinity, then you switch it to a function of x, right? You take your L'Hopital rule, and then whatever that answer is, that's what that does. So this converges to 1/2, right? Okay, let's take a look at it and see what it does. So this is going to be n over 2n plus 1. And, oh, I should have backed this up. Well, take a look at this one, right? So look at the sequence. The sequence is converging to 1/2, right? But think about that. If this is converging to 1/2, and you keep on adding these up, it's just like stacking a half on top of a half on top of a half on top of a half, and you keep on doing that, right? So take a look at this series. The series just looks almost linear, doesn't it? And as I go out here, just take a look at that S sub n. 80, 100, 120. I mean, that thing is exploding, isn't it? So I think it's pretty apparent that this one diverges. Would you agree? And the reason why is because this right here was not 0. Think about it. Let's say that you have a sequence and that goes to any number that's not 0. What would happen? You would just be like taking that number and stacking it, right? So let's see. Give me another number other than this that we could have a sequence converge to. Anything you want. 4? Is that what I heard? Okay, so if I create a sequence, all I'd have to do is change this to 8n on top. I need to back this up. Uh-oh, my computer doesn't like. So look at, so I just changed this to 8, okay? And that way it converged to 4. The sequence converged to 4. So now I'm stacking these up. And as I stack them up, my sum gets huge, okay? How about a negative number? What would happen if it converged to, this one went to 4. What if I change that to negative 8? Wouldn't that change that to negative 4? Would that still diverge? It would be like negative infinity. Yep, look at that. Now, my sequence is not plotting because I can probably change it. But the sequence is converging to negative 4, right? And then the sum of the sequence is actually going to negative infinity this time. So that leads us to our first major way of dealing with series. And it's, I handed out this sheet, right? This sheet contains a summary of how we figure out whether or not series converge or diverge. And this you can have on the test. You don't need it on the test on Wednesday, but on the final you want this. The very first test here is called the Nth Term Test. This is by far the easiest test to actually run out of this whole page. And it's the one you always want to do first. What does this say? This says that if you're looking at a series, now look at how they have this notated. See how that notation on the sheet? What they mean here is an infinite series. So there's really an n equals 1 to infinity there. If they don't write it, it's understood. Now, what does this test tell us? This series, right? Now we're talking about the series. The series diverges if the limit as n goes to infinity of the sequence is not 0. So if you look at the sequence in here, the thing we're adding up over and over and over, if you take a look at that, in the limit of the sequence is something other than 0, divergence is guaranteed. All right? Now, what if your limit is 0? No what? Yeah, what does it say here? It says inconclusive, right? Inconclusive. So we have to be very careful with the logic here. I've given you now 3 sequences to look at. Well, I guess we can do this one, 8n over 2n plus 1, right? This one converged to 4. This one converged to 0. This one converged to 0 in terms of the sequences, right? Now, this one diverged. And the nth term test says that's what should happen. If the limit goes to something other than 0, it's going to diverge. The series will diverge. Now, if the sequence goes to 0, you still don't know. All right? That's the key. You still don't know. The problem that I see students when they misuse this test is they go, oh, okay, I'll just take, oh, it goes to 0. Oh, okay, the series converges then. No. If it goes to 0, then you have to move on and try a different test after that. Okay? All right, so when it comes to series, our goal is going to be to figure out whether or not it converges or diverges. I've said that a few times now, right? Does it converge? Does it diverge? We don't know. Just depends. Now, there are some very special series. Okay? There are some special series that we need to be aware of. And this, I'll just call these our common series. So in the world of series, all right, if you think about all the different series that can be out there, there are a few that are kind of common, and we should be able to recognize them visually when we see them, go, oh, that's a blah. And with these common series, it will be easy for us to determine, well, easy. It'll be within grasp for us to be able to figure out whether or not they converge or diverge. And here are the three common series that we're going to look at. The first one are called geometric series. The next one is called a harmonic series. And finally, in this section, we will look at what are called telescopic or collapsing series. I'm going to say it again. Our main goal is to figure out whether or not a series converges or diverges. All right? That's our main goal. When it comes to the common series, two of these series have something very nice about them. And that is, with the geometric series, if, now this is a big if, okay? If it converges, we can find capital S. What am I saying to you?
Find whether the series converges.
I'm saying something pretty strong here. Let me repeat again. Our goal with series is to be able to determine whether or not they converge or diverge. Okay? If we're looking at a geometric series, if it does converge, we can actually find S. What's S? The number it converges to. Okay? We can actually find the sum. See, I said our goal is what? See if it converges or diverges. That doesn't mean we're going to ever be able to tell you what it converges to. All right? I'm leaving that out intentionally because with a lot of series we can't tell you what it converges to. We can only tell you it converges. And you may say, well, why would we ever care about that? Well, convergence is very important, all right, later on as we move through this. So with a geometric series, if it converges, we'll actually be able to say what it adds up to be. There are very few series that we can do that with. Geometric is one of them. Also, harmonic. If it converges, I just said harmonic, didn't I? Yeah. I meant to say telescopic or collapsing. Oops. Okay, so with a telescopic or collapsing series, if it converges, if it does, we will be able to find its sum. Harmonic series, these series always diverge. So that's why I'm not even throwing these in here, okay? But we'll get to those, all right? So now we start trying to attack these three common series. We'll probably get through the first two today, all right? Telescopic's going to take us at least 45 minutes to get through. All right, so in the common series, we have, let's take a look at this thing called a geometric series. All right, so remember, a series is always comes from a sequence, right? You start with a sequence, then you start adding the things up. So let me show you what the sequence is. We start with A, AR, AR squared, AR cubed, AR to the fourth, dot, 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 dot. Okay? I just gave you a what? What is this called? A sequence. I just gave you a sequence, right? I'm telling you that that is a geometric sequence. So can you tell me what the formula is for this? This is A. So they all have A, right? And then R to what power? N minus 1. Because remember, when you plug in 1, See, this is r to the first power. So this first one right here, you can't really see it, but that's really r to the 0 there, isn't it? Okay, so when I plug in 1, I need r to the 0. So I use n minus 1 up there. And then plug in 2, you get the next one, 3, so on and so forth, right? So do you all agree that this is it? Okay, so that is the sequence. Now, let's take a look at the series for this sequence. The series is the sum as n equals 1 to infinity of ar to the n minus 1, right? It's just take that sequence and, yeah, I'll just do it like that. Take that sequence right there and start adding them up. All geometric sequences look like this, or geometric series look like this, all right? So this is really just a plus ar squared plus dot, 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 and never stop, right? Never stop. So the question is, does this series converge or diverge, right? That's the ultimate question. Does this converge or diverge? And this is actually very tough to just look at and figure out what it does, all right? Because a lot of it's going to depend on what r is. Like, do you agree a is just a number the whole time, right? So what if r was 1? Just out of curiosity, what if r was 1? It would just be a, right? A plus a plus a plus a. And what would that do? Well, the sequence would converge to a, but what would the series do? That would be infinite. That would diverge because if r was 1, right? If r was 1, that would just be a. And that right there does not converge to 0. We're assuming a is not 0. This would be boring if it was 0, wouldn't it? So assuming a is not 0 and r is 1, then it would just be a plus a plus a plus a plus a, and that would diverge. So r is really the determining factor here, like what is r doing? Or how does r impact it? So you can sit here and try and figure out what this adds up to be, and you can probably spend your entire life trying to figure it out. So I'm going to show you how it's done, and I think when you look at it, hopefully you'll get some appreciation for things.
Go over why it's called geometric.
We can talk about a little bit why it's called geometric. It has to do with, you can draw pictures that go with this that are very, using some triangles. If I have time, I will, yeah. Okay, so you ready? Right now, here's what I'm going to write. Okay, what I'm trying to do is figure out, does S sub n converge to something, right? That's what I want to know, right? Does S sub n converge to something? So what is S sub n?
Series.
Is this S sub n?
Yeah.
Nope. What is S sub n? It's the partial sum, right? Remember, remember there were 3 different things that all meant the same thing? Okay, so I understand like this notation, if it's new, this can be confusing. This is what it would mean for the series to converge. If this thing went to something, right? So this thing, we just said, was the nth partial sum. So let's write out what the nth partial sum would be for this. Wouldn't that be the sum? Now, I'm going to stop where? Where am I going to stop this sum? At n, right? So I can't use n down here anymore. I have to use, I don't know, something k. K equals 1 to n of the sequence. A, r to the k minus 1, right? K minus 1. See, it gets confusing because when it's infinity, we're using n here, but then when it's an nth partial sum, we're using n here. I understand this can get messy in your mind, right? Okay, so my question is, does this go to something, right? Does that go to something? Well, let's write out what this is. This side right here would be a plus AR plus AR squared plus, now be real careful here, tell me where I stop. AR so remember here, to get this one I plugged k as 1 here, right? And I got 0. Okay, when I got this one I plug in k as 2. I get this one k is 3, k is 4, 5, 6, and I stop at n. So when I plug n in here, I get AR to the n minus 1. That is the nth partial sum of this, right? And I'm asking myself, what does that go to, right? What does that go to? Which means I need to take the limit of this, right? I need to take the limit as n goes to infinity of this. And that is very difficult to do. That is very difficult to do. Because what happens as n goes to infinity there? Think about this in terms of just arithmetic. If I say stop at n, I can add these up, right? But if I say let n go to infinity, then where I'm trying to add to just keeps going, right? It like keeps running away from me as I try and add them up. So taking a limit of this as n goes to infinity just makes this a longer sum. So how in the world are we going to do this? So you ready for this? This is kind of like, here we go. So someone figured out that this is what we could do. So I'd like for us to write down what S sub n is right now. S sub n, so I'm starting from scratch. I mean, this is the idea, but this is what I'm going to do. I'm going to write out the nth partial sum, which we just said is that, right? Okay, that's S sub n. We would like to take the limit as n goes to infinity. That is that, right? So we would like to take the limit of that as n goes to infinity. But now what I'd like for you to do, and this is just kind of out of the blue, I'd like for you to tell me what r times S sub n is. So I'd like for you to take this equation and multiply both sides of the equation by r. Don't ask me why, just do it, okay? So what would you get on the right-hand side? That times r, AR squared, AR cubed plus. Now down here, leave some room. What would the last one be? A. So I multiplied that by r, that by r, that by r. So the number just kept going up, right? By 1. So if I multiply that by r, I'm going to add 1 to that exponent. So what's it going to be? AR to the n. Agreed? Right? Now, what's the one that would be right in front of this one? AR to the n minus 1, right? That would be the one right in front of it. So the power on r would be 1 less. And then in front of that plus, right? You with me on that? Now I'd like for you to do this. I'd like for you to tell me what S sub n minus r times S sub n is. In other words, I'd like for you to take this row and subtract from it this row. Something really cool is about to happen. Okay, so if I take A, right, I can do these like almost vertically. There's nothing to kill off this A down here, right? There's not an A. Right. So when I subtract, that A is still there. Now, this AR gets killed off by that AR, right? This AR squared, because I'm subtracting. This next one, right? All the way down. Now look what happens here at the end. This one and this one go away, don't they? But this one does not appear up here. So this one is still here, right? But I'm subtracting it. So I get minus AR to the n. That okay? Now, on the left-hand side of this equation, I'd like for you to factor out S sub n. Just algebraically pull it out. S sub n, not equals, S sub n, parentheses, what? 1 minus r equals a minus AR to the n. And finally, I'd like for you to divide both sides by 1 minus r. Okay, we just did something completely Badass is, I can't think of anything better than that, okay? What have we just done? Look at this expression we had for S sub n, right? Look at this expression we had. We said that when we let n go to infinity, this piece would start to march away from us, right? Because we have a bunch of dot dots in here, right? So it's going to start to get longer as we let n go to infinity. But we've found a clever way of rewriting what S sub n is. And now what happens as n goes to infinity? Do you have any dot dots in here that have to like go anywhere? Does this get longer, or you know what I'm saying? Are we adding up a bunch of things anymore? We're not. All that's happening when n goes to infinity is we're raising that number to a bigger power. Agreed? And because of that, I'm going to factor that a out. Because of that, we've somehow turned a partial sum into a very nice, clean algebraic expression, right? Now, let's take the limit as n goes to infinity and see what happens. Okay, so I was wondering what was happening here, and now I'm going to take the limit as n goes to infinity of S sub n, which is equal to the limit as n goes to infinity of a times 1 minus r raised to the n over 1 minus r. And you're going to tell me what that does. Let n go to infinity. What happens? So you're taking that and raising it to a bigger and bigger and bigger and bigger power, right? So all we're concerned with is what happens to that, right? So break out your notes from last class. And we had a very important note there on the bottom of the first page, I believe, when we were talking about sequences. And I kind of jumped through it pretty quick. Do you see the very last thing there? What does it say? The sequence, y'all have this, right, on your notes from last time? The sequence, r to the n. So basically, you know, we're saying what happens to r raised to a power as you let n go to infinity, right? That's what this says. This says it goes to 0 so long as the absolute value of r is less than 1, right? So when we're sitting here and we're looking at this, we're saying to ourselves, all right, yeah. We're saying to ourselves, all right, what happens to this? Well, this is the only thing with n on it, and it's r to the n. So this is either going to go to 0 or it's going to diverge. It'll go to 0 if the absolute value of r is less than 1. So I'm going to say this right here has some conditions. If the absolute value of r is less than 1, then what happens? What would this limit be? The limit as n goes to infinity of a 1 minus r to the n over 1 minus r. What would that go to? Well, the limit wouldn't go to 0. This would go to 0, wouldn't it? And if that goes to 0, then what are you left with? 1 minus 0, right? 1 times a. So you get a over 1 minus r. And that is a concrete number, isn't it? Do you remember in our sequence, when we started, I listed out the sequence. It was a, ar squared, right? Blah, 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 like that. That's what I did. So if someone gives us this sequence, if we can look at the sequence, if we can identify a and r in the sequence, then if the absolute value of r is less than 1, then we know that it's going to converge to a over 1 minus r. Okay? That's nice. Now, what if the absolute value of r is greater than 1? Then what would happen? Just think about if you put a number in here that's bigger than 1 and start raising it to bigger powers. It's going to blow up, right? And this whole thing will become infinite. And so this will be a number, right? 1 minus r will be a fixed number. And then you'll have this divergence. so diverges. So if the absolute value of r is less than 1, we're going to converge to this. Remember I said that with geometric, we're actually going to be able to find what the sum is? That's the formula for it. Okay? Now, if the absolute value of r is bigger than 1, it's going to diverge. Now, what if r is 1? What if r is 1? What would it be if r is 1? If r is 1, what would our sequence look like again? If r was 1, we would have A, and that would diverge also, wouldn't it? Adding those up forever. So that would diverge. There's only one case left to look at. We have absolute value of r less than 1, absolute value of r bigger than 1, r equal to 1. 0 would be this scenario right here. But if r was 0, right, then this would be a plus 0, 0, 0, 0, 0, so it would just be a, right? Make sense? Okay, so what about negative 1? What if r is negative 1? This is the most interesting case, actually, and we're not going to be able to really argue about it too much. But what if r was negative 1? Tell me what this would look like if r is negative 1. No, I've taken these two cases, right? I now am considering if r was 1, it would be a. But if r was negative 1, what would happen? So tell me what would happen. A, and then what? That's negative 1, negative a, and then that's negative 1 squared, positive a. And so wouldn't it be a minus a plus a minus a plus a minus a plus ... Isn't that what would happen? You remember this one? Yeah. What do you think that adds up to be? 0 seems the most logical, right? Or a, right? Why? Like, if you group them like this, that's 0, that's 0, that's 0, right? So it's just like 0, 0, 0. But if you decided to group them a different way, if you did it like this, well, I'll leave that up there. If you did these two together, that's 0, 0, 0, right? But you still have this one left out here, which means that the sum would be a. So is it 0 or a? It's neither and both, okay? So this diverges, all right? This diverges. We'll get to it later. Yeah, we'll talk about it later. Okay, so let's try and summarize this then. The only way we get convergence is this, right? The only way we get convergence is this. If the absolute value of r is bigger than 1, it diverges. If it's equal to 1, it diverges. And if it's equal to negative 1, it diverges, right? So I'm going to put an equal sign under that. And that will cover all the cases. All right? Let's do an example. Find sum n equals 1 to infinity of 1/2 to the n minus 1. Now, all geometric series, I'm going to put this over here in the corner, all geometric series look like this. Right? That's what all geometric series look like. That's what we started with. So is this a geometric series? Yes? Okay, if you're seeing that that's that, then you need to be able to tell me, it's geometric, right? You need to be able to tell me what A is and what R is. You have to be able to tell me